In this lesson, we are going to talk about the big 8 big trig identities, as well as even, odd, and cofunctions. Here are the identities you should know by the end of this unit. You can take a copy of this. You can Google it if you want and find another format of it. But these are going to be very useful throughout this unit. The reciprocal identity comes from when we did right triangles. So when we had hypotenuse, opposite, and adjacent with this angle as theta, I want you to recall that sine of theta is equal to opposite over hypotenuse, and that cosecant theta is equal to hypotenuse over opposite. So just to show the first one, and then you can do it for all the other ones if you want to see them, what sine theta is equal to what it says over here is equal to 1 over cosecant theta. Well, if I put 1 over the hypotenuse divided by opposite, I really flip that fraction at the bottom to opposite over hypotenuse, and that is what sine is equal to. So anytime you have 1 over cosecant, you actually have sine. The quotient identities are very much the same when we're using our right triangles, are proved very similarly. So I'm going to rewrite my triangle up here when we've got opposite, adjacent, and hypotenuse. So here sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. When we divide these fractions, we flip the second and multiply. Our hypotenuses cancel, and we're left with opposite over adjacent. If you remember SOHCAHTOA, opposite over adjacent is tangent. So what this implies is that tangent is equal to sine over cosine. This works for cosine over sine as well. You can pause right now and try to do this one on your own to see if you can, and then turn it back on and try and check your answer. I'll give you a few seconds to do that. Okay, welcome back. So cosine is adjacent over hypotenuse. Sine is opposite over hypotenuse. So adjacent over hypotenuse times hypotenuse over adjacent, opposite. You get adjacent over opposite, and if you remember, cotangent's the reciprocal of tangent. So that's where the quotient identities come from. So now you can use these as you find them useful. My favorite ones are the Pythagorean identities. Okay, if you're writing these notes, I just want you to stop and watch for a minute, and then we'll come back and talk about them. Okay, so the Pythagorean identities are proved a little bit different. I want you to remember, in algebra, as long as you divide everything by the same thing, you're not changing the equation. So we're going to use some of those algebra tricks and tools to help us. First thing I'm going to do, though, is I'm going to write down what sine of theta is, and we're going to call this angle theta. So theta is A over C. Cosine theta is B over C. Okay, so hold on to that. We're going to use that in a second. All right, so the first thing I'm going to do is I'm going to divide everything by C squared. So I get a squared over c squared plus b squared over c squared equals 1, because c squared over c squared is 1. Okay, using the quotient property of exponents, I can rewrite this as a over c squared plus b over c squared. A over c is sine theta, and b over c is cosine theta. Okay, now we could leave it like that, but conventionally we don't write sine squared and cosine squared that way. We actually put the square on the sign or on the function. And this is the first identity for Pythagorean identities. If you want to copy this down, go ahead and pause the video, and then I will show you how to get the other two identities. All right, so for the other two identities, I'm going to focus on the second one. I need tangent. Recall that tangent theta is equal to sine theta over cosine theta. Okay, so what I'm going to do is divide everything by cosine squared. So I'm going to divide this by cosine squared. I'm going to divide this by cosine squared. I'm going to divide this by cosine squared. Because I divided everything by the same thing, I have not changed the value of my equation. It just looks different. So sine over cosine is tangent, and you're allowed to write that as long as you keep the square. Okay, the square doesn't change anything. Cosine squared over cosine squared is 1, and then 1 over cosine squared, if you recall, secant theta is equal to 1 over cosine theta. So the square doesn't affect this rule either, and so we can write this as secant squared theta. We do have to include the square, we can't get rid of it. That is how we get the second one. For the last one, we need cotangent. So recall that cotangent is equal to cosine over sine. So I'm going to divide by sine. The other thing you need to recall is that cosecant is equal to 1 over sine. So I'm going to divide each one by sine squared theta this time. And as long as I divide everything by sine squared theta, it works. So we'll get cotangent squared theta equals cosecant squared theta. Another useful set of trig identities are the even-odd identities. And what these do is they get rid of negative angle measures for us, so that we don't have to go backwards on our unit circle. So here we have sine with a negative angle inside. So I will look at my identities, and these are all true because of the way that the unit circle is set up, and the all students take calculus. If you remember that, you'll see that the sign does change because it alternates around that x-axis. So here we get to say instead it's the negative sine of 30. Well, the sine of 30 is 1/2, so this would be negative 1/2. Cosine goes from a negative to not worrying about the negative at all. And that's because right by the positive x-axis, cosine is positive on both sides. So we get to just say that it's the cosine of pi over 4. This would have been really useful a few units ago. This is the square root of 2 over 2. Now, if you've paid attention to the unit circle at all, you'll notice that this down here at the bottom has a sine and a cosine on all of the fourths of a square root of 2 over 2 square root of 2 over 2 plus or minus depending on where it's located. So what we're going to do first is figure out that this is cotangent of 33 pi over 4, and we'll put the negative in front. Well, cotangent is either, we take cosine and sine and divide it. So cosine divided by sine is 1. So depending on where this is located, if we can figure out what quadrant it's in, we can figure out what this value is. We do know it's going to be a negative on the outside and that this is going to be a 1, but we need to figure out what quadrant it's in. The only way to find out what quadrant it's in is to figure out its coterminal angle. So we've got a negative and we've got to figure out if our 1 is going to be positive or negative. So just recall, coterminal angles is when you take away a full rotation. So we're either going to subtract 360 degrees or 2 pi. Well, since this is in radians, we're going to subtract 2 pi. So we're going to take 33 pi over 4 and subtract 2 pi, and you can do multiples of 2 pi if you want. In order to subtract that, we have to get a common denominator. So if you'll forgive me, I'm going to change this to 8 pi over 4. So this gives me 25 pi over 4. That's still not less than 8 pi. That's what we're trying to get to. 25, so we'll subtract another 8 pi. That'll give us 17. Subtract another 8 pi. That gives us 9. Still not less than 8. And then we're going to subtract 8 pi again and get pi over 4. Well, that's quadrant 1. So my value in here is positive, so that gives us a -1 for that answer. But there's a good review for coterminal angles. Cofunction identities has to do with the fact that a triangle adds up to 180. And when we have a right triangle, then we know one of our angle measures is 90. So we're just going to call these angles A. So if I take A plus B plus C, it has to equal 180. Well, I know that angle C is 90. So I know that A and B have to add up to 90. That means they're complementary. Okay? So hold on to that information for a second while we find this over here. What is the sine of angle A? So here's angle A. If I label my sides A, B, and C, the sine of angle A would equal opposite over hypotenuse. All right, notice that it says cosine of angle B. So I'm going to go over here, and instead of looking at angle A, I'm going to come up here to the top and look at angle B. The cosine of angle B is equal to B over C. No, cosine's not B over C, it's A over C, right? Adjacent and hypotenuse. Well, that's funny because that means they're equal, and that means by the transitive property I can set them equal to each other. So if A plus B equals 90, then the measure of angle B is equal to 90 minus A. I'm going to replace that. Sine of A is equal to cosine of 90 minus A. So now if I'm talking about the same angle, I'm able to say, okay, if the sine of A is 0.23, well, the cosine of 90 minus A is also equal to 0.23. And that's what these cofunction identities are. If you go look at your formula chart that I created for you in your OneNote, you'll see that I've added a few more identities on there for the reciprocal functions too. But there's one of them. You can go through and prove all of them if you want to see if it all works every single time. Okay? So how are these useful? Well, if I have cosine of 27, that's going to be equal to the sine of 90 minus 27. So it says right here. So 90 minus 27, what does that come out to? 63. Okay, if we have it in radians, we can take pi over 2 minus pi over 8. To get our cotangent. So I need a common denominator, and I get 3 pi over 8. So this doesn't seem that useful, right? But watch what happens with this next one, and it doesn't matter if you choose the numerator or the denominator. But if I change my denominator to cosine of 90 minus 54, I get cosine of 36. So sine 36 over cosine 36 is equal to tangent 36. How about that? Now I have one trig function instead of 2 in my equation. What we're going to do with all these identities is we're actually going to simplify trigonometric expressions. When we're doing that, we typically want to get only one trig function, if it's at all possible, and most of the time it'll be possible. We want to get everything down to one trig function. It could be any of the trig functions, sine, cosine, tangent, cosecant, secant, or cotangent, but we just want one. When it's possible, some hints of things that you can use to help you. One of those things is to change everything to sine to cosine. Most of the time that will work, okay? So there are times where it makes it a little bit more complicated, so you got to keep your brain open to other ideas, okay? There may be times where you start these problems and you go, I don't like the direction this is going, and you erase it and start over, and that's okay. If you see a square in it, you're going to use the Pythagorean identities and manipulate them to match the expression. And then the very last thing you've got to check for is that you do not have trig functions in your denominator. Okay. So you might want to get those identities handy so you can see which ones I'm using when I solve these. Okay, so on the first one, what I want to do is change everything to sine and cosine. So if you go look at your trig identities, tangent is sine over cosine. And I'll write that right here. Tangent of theta is equal to sine theta over cosine theta. So I'm going to replace that here. Notice these two cancel, and that leaves me sine theta. So what that is equal to is sine theta. All right, recall that on your trig function, on your trig identities formula chart, that cosecant is 1 over sine theta. So cosine theta times 1 over sine theta is cosine theta over sine theta. This is cotangent theta. You can look at your identities to see that it is under quotient identities. We'll come to B for last. So I want to take a look at D. We've got sine theta, secant theta, and tangent theta. So I'm going to turn all of that over, and it's going to give us a complex fraction, but we might be able to get this to work out. I'm going to leave the tangent theta alone for right now. I'm going to work on the numerator only. I'm going to get sine theta over cosine theta divided by tangent theta. Well, sine over cosine, if you recall, is tangent theta. Well, tangent theta over tangent theta is 1. So it wasn't required for me to change that bottom. I could have, and it still would have worked out just fine, but I didn't have to. right, so one more example on this slide, and I want to show you, notice that it has a square. So the first thing I'm going to look for is on my Pythagorean identities, I'm going to find the one that has cosine in it. Well, the one that has cosine in it is sine squared theta cosine squared theta plus equals 1. But that still doesn't look like what this looks like. So how could I make that happen? Well, if I subtract cosine squared theta on both sides, this is where the manipulation and thinking about what algebra tricks you can use to help you comes into play. I can make this left-hand side look exactly like that numerator. I'm sorry, right-hand side. So this is the same as our numerator. Well, this is also equal to sine squared theta, so I'm just going to replace that with sine squared theta. And take a look at your tangent. On your quotient identity, sine over cosine is tangent, so I can replace this with tangent squared theta. All right, cosecant and secant. We're going to change those over. You should try these. You can pause it, try them on your own, and see how it goes. I'll give you a few seconds to do that. All right, so if you pause and tried them on your own, I'm going to go through and you can check to see how you did. So cosecant theta is 1 over sine theta, and secant is 1 over cosine theta. Dividing fractions is so easy, just flip the second and multiply. So 1 over sine theta times cosine theta over 1 is cosine theta over sine theta, and that happens to be cotangent theta. Okay, cosine theta times 1 over cosine theta over tangent. I'm just going to leave tangent alone for right now. I'm going to simplify the numerator. These cancel, and I get 1 over tangent theta. If you look at your reciprocal identities, that gives you cotangent theta. Now, you may not have worked that one out exactly like I did. It doesn't mean you're wrong. So if you got cotangent theta because you got sine over cosine in your denominator and you flipped it, you're correct too. That's not wrong. All right, sine theta over 1 over sine theta. One more thing on that last one is notice that there's a tangent in the denominator here. I do have to keep going. This is not finished until I get to cotangent theta. All right, so on this last one right here, I've got sine theta over 1 over sine theta. So that becomes sine theta times sine theta when I flip that second fraction, and I get sine squared theta. If you go back and look at the last slide, you'll recall that 1 minus cosine squared theta is equal to sine squared theta. So I'm going to use that and go ahead and substitute that in. So I'll write that here in case you need to see what that looked like. And that's on the last slide. And then we've got sine squared theta times, divided by, sine squared theta over cosine squared theta. Flip the second and multiply, and we get sine squared theta times cosine squared theta over sine squared theta. Those cancel, so we're left with cosine squared theta. Now it's simplified. All right, it's your turn to try on your assignment.